I've been trying to practice doing some more questions before my next full length on Saturday. And yeah, so I got a couple questions. Okay. Yeah, so there seems to be a balancing the equation type of question, but I spent so long trying to balance this, but I'm having a really hard time like understanding how to go about it.
Yep. Let's see. Okay, so why don't you try out writing it and we can go from there.
Okay. Let's see. Yeah, so it's copper. Yeah, it was copper sulfide. So it's Cu, it says 2, but um I think it should just be CuS and then plus nitric acid, so that's NO3. NO3. Oh, I think it should be H. NO3. Oh, I'm drawing a little too big. So copper. It's NO3 minus, but copper should be 2 plus here because sulfide's 2 plus, so it should be um NO3 2 plus it's sulfur plus water and then plus
What's
nitrogen monoxide.
what's
Sorry,
oxidation state or oxidation number for NO3?
-1.
So so wouldn't that change the copper nitrate?
Oh, that's right. Two. Hello? Oh, are you froze?
Oh, yep.
So how do we like go about balancing if it's like this? Like they just put input numbers there in the answer. I was like, I don't know how to where to start from, I guess.
Let's see. So copper 2 sulfide, nitric acid are reacted, yielding copper 2 nitrate, sulfur. Well, what is okay? Sulfur, water, nitrogen monoxide, when 6 moles of copper 2 sulfide and 16 moles. Yeah, so 6 moles of copper sulfide and 16 moles of nitric acid. So now continue the.
Oh, didn't realize that. Okay.
Well, wait.
'Cause I think that's what they're adding, right? The moles. I don't know if that's a coefficient, right?
Sorry. So yeah, you still need to balance the equation. For instance, that you have 2 nitrates here, but only 1 here.
Mm-hmm.
So continue to balance that.
Okay. So but like if it has usually like let's say something like this, where should I like what atoms should I consider first to try to mess around with? Is it
Well,
typically polyatomic or
since you have two nitrates on the right side, you want to put a 2 in front of the HNO3.
okay.
But that also means two hydrogens on the left side, so you're gonna have to change the number of H2O. Oh, sorry,
wouldn't
sorry. H2O.
balance it.
H2O is, yeah, there's two H's there, but you have six oxygens,
Uh-huh.
and you want, and then over here you have six oxygens. Well, actually, then you have an additional one from H2O and an additional one from the NO. And also you have three nitrogens on the right, but two on the left.
Yeah. Two on the left. So I guess two wouldn't work then.
Okay.
Let's see. 1, 2. It's 3 and 8. Could we go with like 24 or something? Because a multiple of 3 and 8, because if we have three oxygens here and we have eight oxygens there.
So we have,
Like, can I put like maybe 24 here? Because even though there's three oxygens here, but there's eight oxygens there.
so
Actually, that doesn't make any sense.
when you put the two here, you then would get six oxygens on the left, and then on the right, we have six oxygens for the copper nitrate, but uh, so there's another one here and another one here, but over here we have two nitrogens, so this could be a two. So now this is two oxygens there, plus six oxygens here to give you eight, and then just one oxygen on the H2O.
This
So
is not
if we make this two, you'd get, let's see,
10.
two over here. Um, Wait, two nitrogens on the left. Oh, sorry, six oxygens on the left. On the right, six oxygens plus two here for eight, plus this. So the H2O has one oxygen, and we aren't going to get an odd number of oxygens. So I would put maybe a two there as well. Um, and then we have on the right six plus two, which is eight, plus two, which is 10 oxygens. And then here, going back for the six oxygens here to get 10, well, you can't get 10 because that's not a multiple. So this could be a three then. Okay.
Okay.
Yeah. So basically, um, yeah, it seems like it's a very exhaustive balancing. So, um, maybe this can help. 6 moles of copper sulfide, 16 moles of nitric acid. Let's see if that can help. 6, 16, 6, 16. Um, yeah, it would just, okay, so Make this a 3, then I have 9 oxygens here. So how about a 4 to have 12 oxygens here, and then on this side we have, okay,
6, 7, 8.
yeah, I would say that, you would just keep doing this until you get it balanced out. Um,
Okay. So it's really just a trial and error at this point.
yeah, yeah. You could say
Okay.
that the difficulty level here is the highest,
Yeah.
and 10% chose the right answer, but over half chose A. So I would say that on the test, this would be a good problem to make a guess, an educated guess on, and flag it and move on. But even when you're reviewing your flagged answers, um, this would still just take way too long to really uh spend any time on.
Okay. Yeah, because when I saw this, I was like, I don't know if I figured it was something where I had to like balance all the atoms, but I wasn't sure if there was another way, like an easier way, but it seems it's just trial and error then. Okay. Um, Another thing was, it was back to this. Oh, how do I? So the question on this specific one, I'm just confused on why it's a passage question, but yeah, I was just confused on why D doesn't make sense here. Like I understand why B would make sense, but I just don't understand why D would make sense. But yeah.
Um,
Look in the first two paragraphs, like the finger domain that they talk about.
Comparison to the transmembrane region of ASIC 1, the finger region. Let's see. Finger region, or 5 domains. Okay. Finger, thumb, blah, blah, blah. Finger and thumb are further from the transmembrane, which means that they're going to be, hydrophilic. So, well, none, so this, so these are like a tertiary structure, which is predominantly consisting of non-covalent bonds, right? Like intermolecular, like hydrophobic interactions, hydrogen bonding, dipole interactions, electrostatic interactions. You know, the only covalent bonds in a protein are the peptide bond of the primary structure and then disulfide bonds, but you're not going to have um oh, and it says covalent bonds that can be broken by exposure to reducing agents. So that's talking about disulfide bonds, right?
Hmm.
But there's no indication that says that the finger region has more or less disulfide bonds than the transmembrane region, right?
I mean, if it's exposed to water, what couldn't we say that? Because transmembrane is more like hydrophobic regions, right? Typically.
Well, you could say that the transmembrane has hydrophobic residues, and the non-transmembrane regions would be hydrophilic residues, but that doesn't tell you anything about whether it has more or less disulfide bonds, right?
I mean, hmm. I mean, if I mean, from that sense, if it has more hydrophobic, wouldn't we say that there's less disulfide bonds? No?
Uh, uh, no. This is a matter of hydrophobic versus hydrophilic. Disulfide bonds don't have any inherent hydrophilic or hydrophobic uh interactions, right? There's nothing that really gives you any indication that we have any difference in the amount of disulfide bonds.
Okay, so basically you're saying like it it doesn't matter because it's like it doesn't really relate to the hydrophobicity or the hydrophilicity of a
Exactly.
protein. Okay. But I
So
mean, I thought I was under the impression that some of the tertiary structure based on like covalent bonds? No?
so there's only two covalent bonds in a protein. One, the first one is the primary is are the peptide bonds that
Mm-hmm.
happen between amino acids, and that gives you a primary structure. And then the only other one are disulfide bonds. Okay. Which means every other type of interaction that the proteins, experience are non-covalent. So that's hydrogen bonding, hydrophobic interactions, etc. So the MCAT tests predominantly your ability to link transmembrane regions to hydrophobic residues and non-transmembrane regions, meaning, either facing the outside of the cell or the inside of the cell, for those to be hydrophilic residues. That's why you'll see this type of thing mentioned in practically every like passage, right?
Yeah.
So they're
Okay.
asking about what makes the finger region different from the transmembrane region. So,
Okay.
in other words, what makes a hydrophobic region different from a hydrophilic region? So, so D, there's no information that lets us know whether something has more or less disulfide bonds. So D is out. C says expected to contain fewer residues that would be protonated at pH 7. That should be the opposite, right? Because if
Mm-hmm.
something gets protonated, it would have a charge. And if it has a charge, it'll be hydrophilic, not hydrophobic, right?
Mm-hmm.
So C is saying that the finger region would have fewer protonated residues. It should have more protonated residues, right?
So it's interacting with the water.
Uh, uh, so, um, yeah, but like, charged amino acids would be located, not in the transmembrane region, right?
Mm-hmm.
So that's what C says. So C is wrong because it should be more residues. Okay.
Oh, okay.
A and B are talking about a change in entropy when immersed in water. So, a negative change in entropy a change in entropy is entropy final minus entropy initial. So if your final entropy is greater than your initial entropy, you have a positive change in entropy, right?
Finals. Okay.
Which doesn't always have to be positive. In fact, it can just mean less negative.
Mm, okay,
right?
gotcha. I didn't think about it that way. Okay, cool. Let's see. Yes. Going over this again. Yeah, I think we can. I kind of understood this, I feel, but now I'm like looking at it, I'm like, "Oh, maybe I don't." Yeah, I think it's something about this graph here, which it's a little confusing for me.
Let's see, we have these okay, pH sensing sites. Um, pH x-axis, y-axis are the y-axis on the left is probability of protonation. On the right are the identities of these residues. So let's see. I'm gonna start at from D at D. So D says at pH 9 over here, most E80 residues would be neutral. That can't be right. The probability is 100% for E80 to be protonated at pH of 9, right?
Okay. I mean, if E80 is protonated, right, you could still technically have um the carboxyl group and the amino group are still they still have their charges, right? So wouldn't that make the protein still like positive?
Uh,
I
well,
mean neutral, sorry, neutral.
no, right? The E is for glutamic acid, right?
Hmm.
So glutamic acid, right, has an acidic side chain, so it would be negative. So you don't have to worry about the C terminal or the N terminal because you're gonna have a Zwitter ion with those, right?
Hmm.
Meaning the C terminal could be negative, the N terminal can be positive, but they cancel each other out.
Right.
So
So you wouldn't say that's a neutral charge? Like a
that
charge
would
of
that would be a neutral charge for a regular amino acid, unless you have a side group that is either acidic or basic. Glutamic acid is called that because its side group has um, an acidic residue, like an acidic portion to it.
Hmm.
Get the negative C terminal, positive N terminal, negative side chain.
Okay. But I mean, but according to this graph, it says that if it's protonated, right? Wouldn't that mean that it's like the O group and then it has the H? So like it would be OH, right? Wouldn't that be considered neutral? No?
Well, so okay, you're telling me that the C terminal and the N terminal make something neutral regardless of the side chain. But if that was the case, we wouldn't have any charged amino acids. We wouldn't have any acidic amino acids. We wouldn't have any basic amino acids.
No, no, I don't no, no, that's not quite. I don't think that's what I'm trying to say. I'm trying to say like basically if both of those sides, like the amino group is positive and then the carboxyl group is negative, right? Like, okay, like sure they're like neutral. And typically, if it wasn't for this case, right? Like I understand that even with the like glutamic acid has a pretty low pK. I think they say right here. So it's like 4.25. So I get why at like pH of 9 in typical conditions it would be deprotonated. But like here, right? I feel if it's if that OH group is protonated, wouldn't that in this situation, like wouldn't that mean that it would be neutral, right?
Well,
I
let's
don't
see.
know if that made any sense.
Okay, no, okay, I see what you're saying. You're saying that if the side chain gets protonated,
Mm-hmm.
right, then
Yeah.
you would make that side chain have a neutral charge.
Mm-hmm.
Okay. No, that's right. You're right. Uh, so I think the accept then would be it, right? This is a true statement.
Oh, okay. So that makes sense.
Mhm.
That makes sense. Okay.
Yeah. But yeah, you're right on that. So good job. It seems like, you highlighted this, so you knew it was a that question, but it's easy to kind of when you're looking at the choices, especially during the test, to kind of like forget that as you go through the choices.
Okay. Mm. All right then. And C says at pH of 7, protonated E239 would be expected to be a weaker acid than protonated D408. Okay. Oh yeah. So I think okay, so that kind of reminds me. Yeah. So I think apparently the reason why this is true is because the E239, if it's more likely to be more protonated, it's more or less likely to want to like give the proton. So I guess that makes it a weaker acid.
Yeah.
And then pH 5, the D346 residue is more likely to be protonated and then would be expected given the pK value alone.
Mhm.
Yeah, because in typical conditions, aspartic acid compared to the pK should be higher. Like there should be more that's wait, what? More likely to be well, yeah, in this residue, yeah, because typically it's more deprotonated.
Mhm.
So, and then 6.1, the D346 is less likely. Yeah, same thing here. It's probably more likely to be protonated. Okay, never mind. That makes sense. Let's see. Not question on this URL thing. Yeah, I decided to just get URL. Um,
Oh, okay.
so I was a little confused about this question. So like I get why like B is wrong, but I don't I don't understand why I'm having a tough time understanding why A, because yeah, wait, let me see what the question says. Yeah, decrease the percent of oxytocin acetate. So I was like, I don't know why it would decrease it.
See.
Remove my strike throughs.
Which of the following experimental changes to the initially prepared oxytocin acetate solutions will decrease the percent of oxygen acetate recovered in experiment 1 after the 4-week storage period. Um, I'm gonna quickly read through this. So let's see. Oxytocin, naturally occurring peptide hormone that is used clinically to prevent postpartum hemorrhage. Um, Heat and light sensitive, requires refrigeration at a temperature below 8°C. In hot climate regions, refrigeration is not available. Okay. To improve the availability, they tried to use buffers and divalent alkaline earth metals to produce an aqueous version that is stable up to 50°C. Experiment 1, to evaluate the effects of the buffer concentration, 2 sets of solutions were prepared containing 0.25 milligrams per ml oxytocin acetate salt in 5, 10, and 50 millimolar citrate buffer solution made from a mixture of citric acid, a weak acid, and sodium citrate, a salt of the conjugate base. An unbuffered aqueous solution served as a control sample using 1 molar sodium hydroxide. The buffered solutions were adjusted to pH 4.5, a pH at which oxytocin is more stable. Okay. And then stored at 5°C set 1 and 50°C set 2 for 4 weeks in a dark area. After storage, the amount of undegraded oxytocin in each sample was determined. Figure 1 using HPLC. Okay. Figure 1, oxytocin acetate recovery in a citrate buffer, 4.5, and water, 6.8. Wait. Oh, okay. So the one in water seems to have, like 55% recovery at 5°C, but like 0 practically at 50°C. And then when you use the buffer, so it seems like the buffer concentration is proportional to oxytocin recovery percent at
Mm,
at 50°C, right?
yeah.
Okay. Um, so let's see. Which of the following experimental changes to the initially prepared oxytocin acetate solutions will decrease the percent of oxytocin acetate recovered in experiment 1 after the 4-week storage period? So what would make it so that, that this, what would make, this go down even more, right?
Hmm.
So, so my thoughts are lowering the amount of, without looking at the choices, my thoughts are either lowering the amount of the buffer or lowering the temperature. Oh, no, no, decrease the amount recovered. So I'm looking at lowering the amount of the buffer and
Hmm.
raising the temperature
Okay.
of the buffer, of the sorry, not of the buffer, of the entire thing. So let's see. I'm going to start with D, increasing the citrate buffer concentration. So that should cause, oh, that would be, so the citrate is the buffer, right? If you increase the buffer concentration going this way, we have an increase in the amount recovered, right?
Okay.
D is out. C, it says storing the solutions at 0°C rather than 5°C. Um, so I'm thinking of two things here. I'm thinking if you reduce the temperature, you should have a higher amount recovered. And you can see that in figure one with the black bars or the dark bars at 5C have a lot more recovered than 50C. So
Mm,
that could be something. But I'm also thinking at 0C, the water should freeze, um, which would also mess things up. But also, solutions have freezing point depression, right? As a
Freezing question.
Yeah, as a colligative property, like if you have compared to water, if you have salt water, let's say, right? Or like that's why they pour salt on the street. Like well, you're in Miami, so but in places where it snows, they would put salt on the ground
Mhm.
because salt would cause the freezing point to drop, which will make it less likely for the for ice to form on the streets. So my thoughts for C are either at 0C it'll freeze, so that won't work, or at 0C it won't freeze because of freezing point depression. But we know if we decrease the temperature, we should have a higher amount of recovery, right?
Decrease the temperature. Okay.
Because 5C it has a lot more recovery than 50C, right?
Okay.
So this should be out as well. B, decreasing the initial concentration of oxytocin acetate. So, okay, let's see. Oxytocin acetate. Ah, if you decrease that initial concentration, sure, you'll have a decrease in the amount of oxytocin acetate recovered, but they're asking about the percent. And also, this is the percent of oxytocin recovered.
Right.
So you
Okay.
might, if you decrease the initial concentration, you might decrease the amount that's recovered, but the percent recovered shouldn't change, right?
Yeah.
So B would be out. And then A, adding more sodium citrate um, after the sodium hydroxide has been added. So we know that we add the citrate, making the buffer before we use sodium hydroxide. But when you use the sodium hydroxide, the pH of the buffered solutions seems to have increased. Let's see. The buffered solutions were adjusted to a pH of 4.5, what makes it more stable. Wait a sec, hold on. Okay, let's see. Okay, so if you add, so when they add the sodium hydroxide, the buffered solutions pH went to 4.5. My thoughts are if you add more citrate after that, it would change that pH.
But my question is like if okay, so if the sodium hydroxide is essentially buffering and adjusting the pH to 4.5,
Yeah.
and we have this solution of the weak acid and the salt of the conjugate base, right? If we're adding more sodium citrate, wouldn't that just end up kind of like balancing out? And like, because if you have more of the conjugate base, because you're in equilibria, so like, wouldn't it just shift to the left and like balance it out? And then, yeah, like, wouldn't that really, like, they wouldn't really be a problem, right?
Let me see their solution, I want to make sure my reasoning is right. Um, let's see. Experiment one, the citrate buffer is made of citric acid and sodium citrate. Adding more sodium citrate to the initially prepared solutions, pH of 4.5, would increase the pH of the solution to be greater than, yeah, okay, yeah, that's what I thought. So my reasoning, oh yeah, seems like my reasoning was works for all of these. So if we go back to D, if you increase the buffer, oh, I mean down there.
Oh, sorry.
If you increase for D, if you increase the buffer concentration, it will, well, we know so that their explanation isn't as good, but we know that if we increase this, we increase the percent recovered, right?
Increase the percent recovered, yeah.
And then C, they said more stable at cooler temperatures. So yeah, it's the thing that I said about that. Like we see that 5C is a lot more percent recovered than 50C. So it would make sense if you go even lower than 5C to have even more recovered, right?
It's more recovered. Okay.
Then B is exactly what I said with percent recovery. If you decrease the initial amount, sure, you'll have less present in the solution and less recovered, but the percent recovered shouldn't change,
Sure.
right?
Hmm.
And then A is exactly what I said. So we know that when they add the sodium hydroxide, the buffered solution pH went to 4.5, which is the pH at which it's more stable. So if you added the um, citrate after you've done that, well, actually, let me see. So they're saying, oh, I didn't even realize the that the citrate buffer has the pH of 4.5 and water has a pH of 6.8. So if you have a greater amount of, so okay, I see. So over here, it's a little misleading because it kind of is telling us that or it looked like it was saying that if you add the sodium hydroxide, the buffer moves to pH of 4.5.
Hmm.
But the figure set shows that if you have the buffer, the pH is 4.5. But if you don't have the buffer, you'll have a pH of 6.8, right?
Okay.
So what seems to happen here is that if you add um, more of the sodium citrate, which is the conjugate base, we should see an increase in pH beyond 4.5, which would decrease the percent recovery of the oxytocin.
Mm.
Yeah.
Okay. Because I mean, like I've learned that typically like the buffer will be able to withstand if like the conjugate base and the acid are like in a 1-to-1 or like 10-to-1 ratio or whatever. But it's a little annoying because like the question doesn't say like how many because like wouldn't a certain if you like I don't know how much sodium citrate they're adding because like if they add a little bit, right, that should still be able to like stabilize it, right? Or is that still my wrong reasoning?
So the buffer is must be a mixture of of a weak acid and its conjugate base, right?
Okay.
But this choice is saying is not saying that we're increasing the buffer because your reasoning is true. For the buffer, if you add more of it, it should resist changes in pH.
Mm-hmm.
But the buffer is the mixture of that weak acid and conjugate base.
Okay.
But choice A is saying if you only add the conjugate base.
I see. So it wouldn't like shift left towards making more like citric acid or something, right? Because I mean like I know they're in like a equilibrium, no? Or
Uh,
that's
correct. So it won't shift left for the citric acid because it'll likely just deprotonate uh whatever molecule that we see. Um, but yeah, the idea is that you're not adding more buffer, you're just adding more base. And if you add more base, you're going to have a higher pH. And if you have a higher pH, you have a lower percent um, recovery.
okay. Sounds good. Okay. And could you explain that like sorry, that last part with the freezing point again? I was a little confused. Like just the overall freezing point, the idea of it.
Oh yeah. So that ended up not even being, you know, a thing here. Because so I was thinking either like, why wouldn't this work, right? So I was thinking three things. I was thinking either it would make you have more recovery because we see that there's an inverse proportion with temperature and percent recovery, right?
Inverse, wait, inverse?
Uh-huh. Like at 5C, we have all these the black bars, which are much higher.
Oh, okay, okay. Sorry. I was stuck on the buffers. My bad. Yes, of course.
So it seems like there's an inverse proportion between oxytocin recovery and temperature, right?
Okay.
So that means that if you brought it to 0C compared to 5C, you
Mm-hmm.
have more recovered or less recovered.
Probably more, right? If you bring it down.
Yeah. So that's logic for that. But I was thinking 0C is the freezing point of water. So maybe, you know, C like maybe that uh wouldn't decrease the amount because, the water freezes or something. So I was thinking that, but then I was thinking of the colligative properties, you know,
He-
in which if you have a solution, you have like your boiling point elevation, freezing point depression, vapor pressure depression, and osmotic pressure. So I was thinking, okay, at 0C, maybe it won't freeze because it has a lower freezing point. So those are just the things that I was thinking of. But ultimately, the
Right.
simplest logic is what wins here, and that's just that if you lower the temperature, you have more recovered.
Okay. Um, but no, I was just generally asking about the freezing point because I haven't seen that in a while, so I was just I just wanted to review it with you. So essentially, the point is, like you said with the salt example, adding the salt, it's adding the salt basically um increases the freezing point, so it takes more it takes a lower temperature to freeze it.
That would mean decreasing the freezing point, though, right?
Yeah, right? Decreasing the freezing point.
Yeah. So I guess I'll just do a quick review of colligative properties. So a pure liquid, like let's say water, compared to a solution, meaning solute, like salts and stuff, can be mixed into that liquid to produce a solution, right?
Hmm.
So what is like, give me okay, so in order to boil something, you must add enough heat to raise its temperature, causing the molecules to move
Okay.
until it reaches the boiling point, at which
Hmm.
that heat contributes to breaking the intermolecular bonds between the water molecules, right?
Hmm.
Okay. If you have a solution with salts, like NaCl would turn into like Na plus Cl minus,
Hmm.
and the H2O, the oxygen of it, is going to make, intermolecular bonds with the sodium ion, right?
Sodium ion. Yeah.
Then the hydrogen will form, intermolecular bonds with the chloride ion, right?
Hmm.
And since the sodium and chloride are charged, it'll produce a pretty strong intermolecular bond, right?
Mm. Yeah.
Relative to the hydrogen bonding between water molecules, like what I just drew.
Right. So you said yeah. So it's going to be stronger bond to the ions than to water. You're saying.
Correct.
Okay.
Now, if boiling point means the heat breaks the intermolecular bonds between water molecules, right?
Hmm.
If you have something that's a salt solution and the water has stronger bonds with the salt, it would require more energy to break those bonds, wouldn't it?
Yeah. Okay.
Okay. So that's um boiling point elevation.
All right. Okay. So you
Now,
need to increase. You need to input even more heat
yeah.
to basically break it. Okay.
Um Now there's also vapor pressure depression. So vapor pressure is like, let's say this is like a container, like molecules of the liquid that are just at the top of this spontaneously enter the vapor phase and just, kind of bounce around like that. Um, and that isn't the same thing as boiling. I mean, in both you have a liquid turning into a gas, but the vapor, we kind of consider it to be less so a gas and more so just, regular molecule of water that just, entered that vapor phase.
Okay.
Which means that but it still has to break intermolecular bonds with other water molecules, right?
Right. Then how is it able to? It just spontaneously does that?
Yeah, yeah. They'll spontaneously do it, um, just because, I guess the ones on the surface, the ones that are under the surface can have more water molecules around it to bind to, but the ones at the surface only has water molecules like under it to bind to. But yeah, if you overcome those intermolecular bonds between water molecules, you'll have more of those water molecules entering the vapor phase.
Okay.
So now, if the water molecules have a stronger bond with the salts, it'll be harder for the water to exit that liquid phase to become vapor, right?
Hmm.
And vapor pressure is just the pressure that pushes against the water caused by that vapor. So if you have less vapor made, you have less vapor pressure,
Okay. Cool.
right? And then freezing point depression, if you have, so the unique thing about water is when it forms, like, so you know how water, what's unique about water freezing?
What's unique about water freezing? Uh, I guess it can freeze and then it can also melt, I guess.
So
Like
what,
they can form pretty quickly. Well, not quickly, but they can break and form, I guess.
so what for a typical thing, if so like, anything that isn't water, if it's solid, is it more or less dense than liquid?
It's typically, if in the solid state, yeah, it's typically more dense, right?
Yeah. Now, for water though,
Mm-hmm.
the solid phase is less dense, right? Like that's why ice floats in water.
Mm-hmm. Yeah.
What's up with that? Why does that happen?
Yeah, because I guess the cube is just less dense than the water.
Yeah, like why, when it is a solid, does it become less dense?
I'm not quite, I'm not quite sure.
So, like everything, water's unique properties have to do with its bond geometry and its bond geometry, which is, that bent shape,
Mm-hmm.
means that it will produce. I'm going to put a picture in the chat. So, okay, put a picture in the chat. So you could see that, like, let's start from right to left. So steam, you know, obviously involves breaking those intermolecular bonds. So you just have the molecules, further away from each other, right?
Right.
For water, for the liquid water in the middle, you see that molecules start to get closer together, and you see hydrogen bonding being, like here, right?
Mm-hmm.
That's your liquid phase. But your solid phase, because the water has that bent structure, in order for it to produce the hydrogen bonds, it has to be in this hexagonal crystal lattice,
Okay.
which means that you could see that it's a far less dense, right? Compared to liquid water in the middle.
Or less. Just because of this, just this, the structure makes it less dense?
So like the water molecules are pretty close together, right?
Uh-huh.
Here, they're pretty far apart. You have this entire open
Okay.
space here.
I see what you're saying. Okay.
So that's why solids typically will get more dense, but for water, the solid becomes less dense because it must produce this crystal lattice structure, hexagonal crystal lattice structure.
Cool. Okay. That makes sense.
So that's just why solid water um
Distance.
is less dense. Yeah. Now, same thing with colligative properties. If you had salts in there, it's going to interfere with the bonding of water to itself,
Mm-hmm.
meaning it can like enter in, like, you can have like a sodium like ion here. You can have a lot of these impurities that make it so that these bonds uh become harder to make.
Mm-hmm.
That's what gives you your freezing point depression. Okay.
Gotcha. Okay, that's cool.
Yep.
Nice. Awesome. All right, yeah, that was easy.
All right, awesome. So, yep, you can just send over 75, and I see you next, I guess, next week.
Yeah, I didn't do the
Okay. Yeah.
I can do the math then. By the way, if you don't see me, then I'll call you. Do you want me
Um, can you use my Calendly?
Oh, okay, yeah, sure.